So on 25, how many, help me out again, how many people did they say they had applying for the engineering spot?
12.
12?
Yeah.
And how many applying for the
Manager is like 17.
17? So if we took Joe from this one and Sally from this one, we could pair them together and we could go through and make up 12 names and 17 names. No reason to do all that. If we're just looking for total possible ways, all we do with these two is what? Times. Somebody help me out, what's 12 times 7?
Where does that
17.
matter?
204 different ways that they could fill the positions. So what's the probability, they didn't ask us this, what's the probability that we pick Joe and Sally for the two positions?
204.
This is the answer, but if we were wanting to change it or figure out a probability, we could do that. Next question. Probability is easy.
$41.
41. A probability experiment consists of rolling a 6-sided die and spinning the spinner shown. The spinner is equally likely to land on each color. Use a tree diagram to find the probability of each event. Then tell which event can be considered unusual. All right, first thing, I don't want to draw a tree diagram. Is that all right with everybody? Or do you guys want me to draw the tree diagram? Decide, I don't care. No, all right. Nothing else, I would list the sample space. So we could roll a 1 and get what color?
Red.
We could roll a 1 and get what color?
Yellow.
Could roll a 1 and get what color?
Green.
Could roll a 1 and get what color?
Blue.
And then what else are we gonna have for our whole sample space?
2 red.
2 with all the same thing, 3, and I'm gonna do that. So give me just a minute here. When you get stuck on a problem, might not hurt to write this out. Thinking well today.
4 red, yellow, 5 red, 5 yellow, 5 green, 5 6 red, 6 yellow, 6 blue.
So how many total items in our sample space?
24.
So that'd be our bottom number if we're doing any probabilities. We can just run down 41 through 44, we probably do them all fairly quickly. Rolling a 5 and spinner landing on blue. 1 out of 24. Now, they wanted to know if that's unusual or not. Well, to tell if it's unusual, has to be 0.05 or less. So you need to grab your calculator and divide that as 1 divided by 24, 0.5 or less.
0, yeah. 0.042.
0.042.
Yeah.
So would that be considered unusual?
Yeah.
Unusual. So remember, it's 0.05, not 0.5. Make sure you don't make that mistake. If it's less than 5%, if it's less than 5%, then it's considered unusual. 42, rolling an odd number and the spinner landing on green. So an odd number in green. Which ones are favorable outcomes?
1, 3, 5.
With the green, right? So how many of those are there?
3.
3 out of 24. Somebody help me out with the calculator. What's that as a decimal?
0.125.
So about 12.5%. Is that unusual? 43. What's 43 say? Rolling a number less than 6 and the spinner landing on yellow. So a number less than 6 and yellow.
It's like 5 out of 24.
So it's that one, that one, that one, that one, that one. So 5 of them, 5 out of 24. Is that going to be considered unusual?
No, it's not.
It's going to be higher than this one, right? So not unusual. 44. Not rolling a number less than 6 and the spinner landing on yellow. So not rolling a number less than 6. What's that telling us?
It's gotta be unusual.
It's got to be a what? What number?
6.
It's got to be 6. So the only one that works is that one there. So that's 1 out of 24. And that is same as that first one, so it is unusual. Next question. Just ready to move on to the harder stuff? Get ready to show you. All right, with probabilities, lots of different ways you can do probabilities. And that's what makes it sometimes a little more difficult. You have stuff like conditional probabilities. With conditional probabilities, you start getting into stuff where you have to decide, hey, what am I using here? And that's when it gets hard. So when we take the test over this chapter, it'll sort of be tough because you're going to have to say, all right, which thing am I using here? Am I doing conditional probabilities? Is it just regular probability? Is it that there'll be other things as we go throughout this that you'll see? So it makes it sort of tough sometimes because you have to decide, all right, how am I doing this? What we're going to deal with today, determine conditional probabilities, and you might title, if you're titling this, just conditional probabilities. Distinguish between independent and dependent events. Anybody have a guess what the difference between independent and dependent events is?
Independent on its own, and it has some sort of variable attached to it.
Sort of. All right, and we'll talk about that. Sort of on the right track. Use a multiplication rule to find the probability of 2 events occurring in sequence. Use a multiplication rule to find conditional probabilities. Again, the main thing today, conditional probabilities. What's the word conditional mean?
It has a condition.
All right, it has some kind of condition. So if I say, I want to pick a male student from all of your names, that's a conditional probability because I'm only picking from what? The male names. All right, so there's a condition. We're only picking from the male students. Conditional probability. Get this up here. Too far. Of course. Conditional probability is denoted probability of B. This right here means given that, and whatever the second thing is, given that A has already occurred. So if I had all your names in a hat, and I said I want to pick Cooper's name out of all the male names, it would be probability given that we pick Cooper, given that we're only taking from the male names. And that's supposed to be a backslash like, so it should look like this. I'm not sure why it looks so straight up and down. Probability of B given that A has already occurred. Again, where this gets tough, those two events could be independent of each other. They could be dependent of each other. Probabilities that we deal with in this chapter, you'll use your calculator to do the basic math, multiplying and stuff like that. But when we get to other probabilities later on in the book, there'll actually be programs and stuff on your calculator to do stuff. But most of the stuff this time, there is no real program like there was for last chapter, where we stuck it into the list and it calculated everything for you. Got to make sure you don't get these confused with, last time we talked about it, you could just do like the probability of getting B. That's what that is. You could do the probability of getting B and A, and we'll talk about stuff like that as we go. You could deal with probability of getting B or A. So lots of different setups, and you got to decide which one you're using as we go through these probabilities. Two cards are selected in sequence from a standard deck. Find the probability that the second card is a queen, given that the first card is a king. So we're doing the probability, it's going to look like this. We want the probability that we get a queen, given that we've already taken out one card and it was a king. This is a conditional probability. So we've already selected one card and it's laying here on the desk, and it's a king. What's the probability that we draw a queen? Does everybody understand the deck of cards? Last year, a lot of the students didn't know anything about deck of cards. Should we go through them real quick? Everybody understands a whole deck of cards, so let's just do some stuff then. How many queens in a deck of cards? Four. There's four of everything, right? How many different suits? Four. What are they? Hearts, clubs, diamonds, spades. All right, so those four. Two of them are red. Which two are red? Diamonds and hearts, and the other two are black, which are clubs and spades. How many cards in each suit? This is the one that nobody usually knows. 13 cards per suit, so there's 13 hearts, 13 clubs, 13 diamonds, so on and so on. How many face cards in each suit? Three. What are they?
King, queen, jack.
King, queen, and jack. Don't think an ace is a face card. It's not.
Is it just like a normal card?
Ace, yeah. As a matter of fact, when they print out decks of cards, ace doesn't come at the king side. It comes at the first side because it's the number one. But for some reason, most card games consider it the highest card. So on this, if we're trying to draw a queen, how many queens in the deck? 4. Now here's where you gotta be careful in this one. How many cards are there in the deck?
52.
Well,
51,
52,
because you
but,
took the king out.
yeah.
We got the king laying out here, right? So now there's only what left?
51.
51. So that's our probability, 4 out of 51. So you gotta make sure it's conditional because you already took out one of those cards. They did the math for us there. Would that event be considered unusual?
No.
So getting a queen wouldn't be considered unusual at that point. A lot of times conditional probabilities, we do stuff like this, where we're using a chart. The table shows the results of a study in which the researchers examined a child's IQ and the presence of a specific gene in the child. Find the probability that a child has a high IQ given the child has the gene. We can tell that they didn't do you guys right because all of you would be up here, right?
Yeah.
So, find the probability that the child has a high IQ given that the child has the gene. So we want this. Probability high, given we already know what?
And then the gene.
They have the gene. So, here's where you gotta be careful. We're only picking from which children?
The gene present.
The ones with the genes. We're only picking from those. How many of them are there?
72 total.
72 total, so that goes on bottom. Because we're only picking from those, we're not picking from the whole 102. Because we're saying we're just picking out the children that we know have the gene. And what's the high IQ? How many of them have a high IQ?
33.
Now again, numbers like this, I probably won't throw a big fit if it was on a test and you left at 33 out of 72. But usually if you're going to tell somebody, yeah, 33 out of 72 that have the gene have a high IQ, that doesn't tell them anything. So you might want to change it to a decimal or a percent. And that would be a better number for whoever's looking at it next. And that's 0.458, so about what percentage?
45.
About 45, 46%. If they have the gene, then they're going to end up with a high IQ. Does it look like that the gene actually is a cause for the high IQ?
No.
Not necessarily. It's about right at 50-50% chance that you are there. Independent events. Independent events, the occurrence of one event does not affect the probability of the occurrence of the other event. As you're writing this down, when we just did probability of getting a queen, probability of getting a king, or given that we'd already gotten a king, did us drawing out that king affect the probability of getting a queen?
Yeah.
Yeah, I made one less card in the deck. What could have changed that would have caused it not to affect getting the king, getting the queen?
Put it back.
If you put the card back. So that's another thing that they could screw with you and say, you take out a card and you put it back, then the two events are independent of each other. But if you take out the card and you keep it out, then the events are considered dependent of each other. So independent events, the two events don't affect each other. Ebersole genes, probably. I don't know, that would involve me giving my opinion. In my opinion, every baby is born with a brain that weighs, what, like 2.5 pounds or something? I don't know what it is, you just look it up, every baby's born with the same size brain. So, all these students that I've had over the years that say, well, my mom and dad were stupid, that's why I'm stupid. Bull crap. I mean, that's probably a cause, but it's not a good excuse. My mom dropped out of school when she was a sophomore in high school, and my dad dropped out when he was in 7th grade, so I went to college. What's that got to do? So when you're looking at this second thing here says probability that we get B, given that that A's already occurred, is the same as just the probability of getting B. All right, so if we want the probability that we get a queen, given that you drew a king, but we did what with that king? Put it back. This probability of getting the queen, given that we drew a king, if we put the king back, is going to be the same as just doing the probability of getting a queen. All right. So that would just be if we put it back, that would just be 4 out of what? 52. Does anybody know what 4 out of 52 reduces to? 1 out of 13. Using there's 13 cards in each suit. That's the way it reduces. I would probably, if I was doing something, I would probably leave it 1 out of 13, because that tells whoever looks at it, do it 13 times, you're going to win how many times? Once. A dependent event is like what we said on the other one. If we took the king out and we kept it out, then the probability of getting the queen is dependent on what we drew the first time. What would the probability, maybe looking at dependent events, this is probably the easiest one to look at. If we're playing some card game and we want to get 2 queens, and we already have 1 queen in our hand, what's the probability of getting a second queen if we keep that queen in our hand? 3 over 51. So that makes it go down. It's dependent on what happened here. Draw 10 from a deck of cards and draw another 10 from a deck of cards. So again, what did they not tell us here that we need to know?
Put the card back.
Whether we're putting it back or not. All right, so if we're putting the 10 back, then they're independent of each other. If we're not putting it back, then they're dependent on each other. Decide whether the events are independent or dependent. Select a king from a standard deck of cards, not replacing it, and then selecting a queen. We've already decided that is what? Dependent. And we figured out what the probability was already. It was 4 out of 52. Tossing a coin and getting a head, then rolling a die, a 6-sided die, and getting a 6. Independent or dependent? Independent. One doesn't affect the other. If we toss a head, that doesn't mean that we're going to get a 3 on the die or anything like that. So they're independent of each other. Multiplication rule for probability, and this one's sort of important. Not sort of important, it's really important. notice here, when we start off, it's got the word "and" in it. So you want probability A and B occur. It's probability the two events will occur in sequence. What's sequence mean?
One after the other.
One after the other. So apparently you're doing what? Are you doing just one thing here?
No, you're doing
Apparently you're doing two or more. And this looks confusing. Don't make this more confusing than it is. This is the probability of A. This is just the probability of B, but you gotta take into consideration that event A has already happened. So whatever that event A was, it's already occurred. So if I put all your names in a hat, and I wanna draw out two females' names, cause I don't like the guys in here, they're all a bunch of knuckleheads. Alright, so I put in everybody's name and I wanna draw out two females, and I draw out Gwen's name, and then I wanna draw out Thelma's name. That's what we're doing here. What would the probability of drawing out Gwen's name be?
1
Now remember, I want to draw out a female name. Does that say I'm not throwing the guys' names in there? I'm being a jerk and keeping their names out? No. So how many people in here?
10.
So and then how many females in here? So that's the probability of drawing the first female times. If I draw out Gwen's name, it's out now. Now it's 2 out of, be careful, 2 out of 9. Probability of B, probability of getting Thelma's name, given that we've taken Gwen out, and you just multiply those. On top, 2 times 3 is what? 6, it's not that hard. 10 times 9. And you could reduce that down, again, on your calculators, if you just wanted to reduce something down, there's a math button. Use that math button. You just type in 6 divided by 90.
So could you reduce down to 2/9, like already?
You could reduce it down before you do this. So, like if I'm looking here, what'll go, remember you gotta cross reduce.
Oh, yeah.
What'll go into both 3 and 9?
3.
3 will go in 3 once, 3 will go in 9, 3 times. What'll go into both 2 and 10? 2 will go into 2 once, 2 will go into 10, 5 times, and we multiply what's 1 times 1. 1, 5 times 3. So what's the probability that I draw out Gwen's name and then Thelma's name? 1 out of 15. Would that be considered unusual? We need to change it to a decimal, right? What's 1 over 15 as a decimal?
0.067.
So would it be considered unusual? No, it's close, but not.
Wouldn't that be the probability of just drawing any female's name? Because wouldn't
Right.
Gwen just be 1 out of 10?
Right.
And she'd be 1 out of 9.
So if I wanted to switch it up and change
Okay.
the names, yeah.
Great. Because whenever I saw 3, I was like, there's 3 twins in here.
No, there's, 3 females. Yeah, so you're right. The way I was saying it, I guess if we just wanted to do probability of Gwen and Thelma, then the probability, instead of being 3 on top here, would be what? 1. So it'd be 1 out of 10, and then what's the probability of getting Thelma? 1 out of 9, and that would be 1 over 90. Yeah, that's your, I said it that way at the beginning, and then I changed it because I threw in names, and I shouldn't.
I was wondering what happened.
Let's see, we saw this. If they're independent events, if the 2 events don't affect each other, then all you're gonna do is take the probability of A times the probability of B, that'll give you your overall probability. So if we were rolling a die, flipping a coin, two things don't affect each other, they're independent, you just multiply the two probabilities to get your overall probability. Can be extended for any numbers, just like the rule that we learned last time. So if you had 6 events, 7 events, just multiply by the next one, multiply by the next one, so on, so on, so on, out as far as you need to get them. 2 cards are selected without replacing the first card from the standard deck. Find the probability of selecting a king, then selecting a queen. We've already done this, so I'm going to go through this sort of real quick. Probability of selecting a king was 4 out of 52. If we keep the king out, it's 4 out of 51 for the next one. We multiply those two together, and you get 16 out of 2,652, and that ends up being 0.006. So that's really unusual, isn't it? So if you ever watch any of these poker shows on TV, which they're not as big now as they were a few years ago, but still quite big, and I watch them all the time just because if you ever watch them, you'll see the people on there that are playing.
They're funny looking.
That might be, but they're very, very, very intelligent. You hear them talking about them. Oh yeah, John dropped out of Harvard to play poker for a career. He had a full ride at Harvard and scored a 36 on his ACT and a 3,200 or whatever on the SAT, but he dropped out because he wanted to play poker forever. Very, very intelligent people.
It makes me cash.
All right, now, yeah,
This
so-
ain't looking too hot, I'm gonna be honest.
So, yeah, it looks like they make cash, but they don't show how many tournaments those people actually play and pay $10, $15, $20,000 every time they play, and how they show them, going to the finals maybe once out of a whole year.
Yeah.
Listen when they tell their overall. This person's made $300,000 and he's like 70 years old. He's made $300,000 over the last 40 years or something. That's not too great.
Yeah, no, I'm out.
On this one, you and a friend are playing Texas Hold'em. So if you know anything, and if you don't know, again, Cooper, don't go home and tell your mom. I'm showing you how to play a game or whatever. You're playing Texas Hold'em poker. With Texas Hold'em, the way it works, you get 2 cards in your hand, and then you get 5 cards turned up down here, and you use the best 5 cards out of the 7 that you have, the 2 in your hand and the 5 on the board. So you and your friend are playing Texas Hold'em. This is your hand, that's your friend's hand. Right now your friend has what?
His wrists. It's not free here. He needs 2 kings in his hand. Right?
No, not with Texas Hold'em, that's with like Omaha or something.
Three's a kind.
He's got 3 of a kind right now, all right? So he's got 3 kings right now. You have what right now?
Ace high.
Ace high. So you really have not a whole lot of anything right at the moment, all right? What do you need to come up for these next 2 cards to help you out? Ace on the first one? How about on the second one?
Probably
Another ace. If you get 2 aces, then you will have 3 aces and 2 kings, which is considered a full house. All right, so you have 3 of a kind and 2 of a kind. He also has a full house, but if there's 2 aces up here, he'll have a full house, but his will be kings and aces. Yours will be aces and kings. Well, yours will be the better hand then, all right? Because you have 3 aces and 2 kings. He has 3 kings and 2 aces. So yours would be considered the better hand. But that's the only way you can win here. So what's the probability of this card being an ace. Think carefully here before you, so we need an ace and an ace. That's what we want. And just take into consideration, you're the only one playing. You and your friends, the only two people playing. There's nobody else playing. So what's the probability of getting the first ace?
1 out of 45.
40, where'd you get 45 at?
Subtracted all the cards like
All right, there's 52 cards in the deck. You got 1, 2, 3, 4, 5, 6, 7 that you already know, right? So we're gonna get rid of those because they can't come up again. So that's 45. Now be careful. Is it 1 out of 45? It's 3 out of 45, right? Because there's still 3 aces left in the deck. Now, what's the probability that you get, so let's say this one works and you get that first ace, what's the probability you get that second ace?
2 out of
2 out of
44.
44, everybody agree with that?
Yeah.
I can do the top, that's 6, somebody help me out and do the bottom. 1980. Now do this for me, 6 divided by 1980, tell me the decimal.
3.03, the 03 is repeating, e to the negative of 3.
So it's like that, right? 10 to negative thirds, that tells us do what to this decimal?
Move it left.
3. So that'd be 0.003.
I like those odds.
I don't.
As a percent, what's that telling you as a percentage? 0.3%, not 3%, 0.3%, so less than 1% of the time.
I'm not gonna lie, I would have folded instantly.
So is there a good chance you're gonna win there?
No,
Probably not.
I wouldn't even test the check, I'm just gonna fold it.
Now, what I was talking about, those people who play this, and you'll see some of them and they're not this way, but you see a lot of them, they figure up all this stuff in their head. They know this. So if you're ever watching those on TV and they'll say this guy's got a 40% chance of winning, this guy's got a 60% chance, and this person, so on and so on. Those guys know this in their head. They can figure it up in their head. That's what makes them good at this. Because then they, not only do they look at that, hey, what's my odds of winning here? So let's say their odds of winning is that less than 1%. What might make the guy call here?
That first ace turns up.
Maybe. But another thing is that they look at how much money's in the pot. Am I getting, you know, if for some reason they've only put in 5,000 and there's 50,000 in the pot, they're getting 10 times their money, that might make it worth doing that. And they figure all that in their head. They say, okay, so my odds here, my probability's not good, but the return on my money is 20 times as much as I put in.
The risk over reward.
Right.
And then yeah, because it's not gonna be an ace, it's gonna be like,
It's gonna be a 3.
yeah, it's literally just gonna be like a 3 spades.
So when you see stuff like this, and you see, if you're watching those games, and when I watch them, I think, man, why are you doing that? But somebody gets like a pair of deuces. So they get a pair, that's the smallest pair you can have. And they're betting a bunch of money. I'm like, why are you betting? That's the smallest pair you can have, why are you betting a bunch of money? The reason that they're betting a bunch of money is because the probability of getting any pair is 4 out of 52. First card could be anything. Times 3 out of 51. Somebody help me out, do the bottom there. 652.
Yeah.
Divide that for us. 12 divided by 2,652.
0.004.
So if I'm looking at this, what this says is 4 times tens, hundreds, thousands, 4 times out of every 1,000 hands, you're gonna get dealt a pair. So if you get dealt a pair, it's a pretty big deal. Because it's only gonna happen 4 out of every 1,000 times. So you sit there and you play 1,000 hands, 4 of those times you can expect to get a pair. That's why any pair,
Is
they
that
end
what
up
they
winning.
mean by when they count cards? Or is that different?
Counting cards is different, because with counting cards, if you're playing like blackjack, counting cards, what you're doing is you're giving all the face cards and tens, you're giving them a value, so face card might count as a 1, I'm not sure, I've never counted cards, but you give it a value of 1, and then every other card, so 2 through 9, you give it a certain value. A lot of times, I think it's like 0, and they count them so that they can see what's most likely to come up next. Is another face card likely to come up? Is a 10 likely to come up? Is an ace likely to come up? And so they're counting how many cards are in that. And if you're playing with just one deck, counting cards is pretty easy. If you're playing with
5 decks.
5, 6, 7 decks, then it makes it a lot more difficult.
Because they normally do like 10s. I know some cards are like 13 or 16. Because then it makes it easier to count multiple decks.
This is just all the aces. 0.03. So again, what that means is if we play that same hand over and over again, we're gonna win 3 times out of every 1,000 times it's dealt. So your friend's gonna win 997 times out of every 1,000. The coin is tossed and a die is rolled. Find the probability of getting a head and then rolling a 6. So probability of head and a 6. First, what's the probability of getting a head?
1/2.
Times, what's the probability of getting a 6?
1/2.
Do they affect each other? So they're independent of each other. Probability of getting a head and a 6, 1 out of 12. Or about 8% of the time. Probability that a particular knee surgery is successful is 0.85, or 85% of the surgeries are successful. Find the probability that 3 knee surgeries are successful. So this doctor's got 3 knee surgeries all in one day. He's operating on poor Chase's knee. It beats it. Tell Cooper to start blocking better.
It ain't me, brother.
So, probability that a particular knee surgery is successful, find the probability that all 3 of them are successful. So we could set up, we want probability of success and success and success. What's the probability that you get the first success?
I got
0.85. What's the probability you get the second success?
1/12.
Probability you get third success. What are you gonna do with all 3 of those? Somebody multiply all those together. So this doctor's doing 3 surgeries all in one day. What's the probability all 3 of them are successful?
0.6358.
So about 63, 64% of the time, if he does 3, if they do, I don't want to be a male chauvinist here. If they do the surgery, 63% of the time, all 3 of them are going to be successful.
That's not good.
That's not really good.
That's the feast choice.
Let's do this just before I go on. What's the probability all of them are failures? What's the probability the first one's a failure? 0.15, good. What's the probability the second one's a failure? Probability the third one's a failure. Might multiply all those together for us. So his doctor comes in and is having a real bad day,
Didn't just call me.
maybe.
0.003.
So again, less than 1% chance that all three of them are gonna not go well. I think it's 614, you guys got 638. You guys multiply wrong on me. Find the probability that none of the three surgeries are a success. We just did that, 0.003. Please remember, what's this called? This 0.08 or 0.85 and 0.15. Those are called what to each other? All right, they're complements of each other. They add up to one whole. Now is when we get into a little tougher stuff. Find the probability that at least one of the three surgeries is successful. So we want the probability at least one is a success.
So then we just look at the probability of one of them.
So at least one of them, it would just be 0.85 then?
Because if you're only looking at one in specific, then wouldn't you just look at that?
Well, it's saying at least one, so we still have to look at the other three.
So you could have what?
So you have a higher probability, right? You have a higher chance of at least one being right.
Should have, it seems like, right? Because at least one would be better than all three of them. So if it's at least one, what are we looking at? Probability that how many successes? One or two or all three. So we're finding the probability that one was a success, probability that two were a success, probability three, and we're putting those all together. How would we do that? There's an easy way to do it. We just did it on the last slide, sort of. What are we not looking at? Probability that you don't have what? All failures. So if we take probability all failures, we said that was what? 0.003, is that right? If we listed all these, I came out here to the side, we got these three things. You could have success, success, success. You could have success, success, fail. You could have success, fail, success, right? Is that all of them?
No.
Success, fail, fail.
Success, fail, fail. So that's all with S in the front, right? I don't know why I separated that one off from there. Then what could we have?
Fail, success, success.
Then,
Fail, success.
then,
Success, fail. Oh wait, no, we already had that.
There we go.
then what? Fail, fail, fail.
So,
Is that all of them?
well, no, because we got.
So, problem that you have here is, we're looking at it like, this is the first surgery, this is the second one, this is the third one. So would there be more than this if we were looking at it different? Yeah. So we could, but we could list out this whole list like we did with the list for rolling 2 die and figure out which one. But the easier way, if they're all failures, what's the only thing left that's not all failures? What are the probabilities that are left not all failures? How many successes? You could have 1, 2, 3, right? So if we did all the failures, which we did a second ago, everything else other than the failures is one success or two successes or three successes.
So 99.7.
So all we'd have to do here is take 1 minus that, 1 minus 0.003, and what's that come out to be? So the probability of getting at least one success is almost 100% of the time. That doctor's gonna, they do 3 surgeries in a day, they're going, at least one of them's gonna be successful.
Pretty good.
So make sure you're always looking at stuff like this. Don't make it harder on yourself than it has to be. Think about, okay, what's the easiest thing to find here, and can I use that to help me find what I'm looking for? We could have went through and figured out what's the probability of getting 1 successful, what's the probability of getting 2 successful, what's the probability of getting 3 successful, found all that. Then we'd have to do something with them that we don't know yet, and we could have done it that way. Much more work. More than 15,000 U.S. medical school seniors applied to residency programs in 2007. Of those, 93% were matched with a residency position. 74% of the seniors matched to a residency position were matched to one of their top 2 choices. Anybody have any idea what that's talking about?
No.
All right, when you go to medical school, you gotta get out and you gotta do an internship or residency. So you gotta go work somewhere and you sort of work for free, and they about kill you, because if you're working for free, they make you work a lot of hours. So you get out and you go do your residency, you get a pick, all right? I wanna go be a resident, be an intern here or here. You get 2 top choices. Now, you don't always get your top choices, and you notice here, it says 74% got their top choices, or one of their 2 top choices. Medical students electronically rank the residency programs in their order of preference, and the program directors across the United States do the same. The term match refers to the process where a student's preference list and a program director's preference list overlap, resulting in the placement of the student for a residency position. So that's what I was just trying to explain there. All right, so they got one of the places, maybe they want to go to Reed because it's close, all right, or they want to go to Dayton Children's, for whatever reason. Find the probability that a randomly selected senior was matched with a residency position and it was one of the senior's top choices. Would they say, first of all, how many of the seniors were matched? It was 93%, wasn't it?
Yeah.
What's that as a decimal?
0.93.
0.93. And then what ones got one of their 2 choices? It was like 74%, so 0.74. What do you think you're going to do with those 2? Multiply them together. You end up with 0.68, so about 68, 69% of all medical students got matched and got to go someplace they wanted to go. What happens here, let's talk just about this, the 93%. What's left out there? 7%. So 7% of medical students. Josh goes to medical school, and for whatever reason, maybe his professors don't like him or something. He might be one of those 7% that they say, you know what, he's just kicked off to the side, and he's got to fend for himself and might never find a residency, and then he's wasted 6 years of his life going to medical school because he can't do his residency, and he's out of luck. Find the probability that a randomly selected senior that was matched to a residency did not get matched with one of the senior's top 2 choices. So this time, instead of doing what we did there, we're going to do what we were talking about a second ago. And the ones that did, subtract that from 1. and we get 26% of them. The assignment's on page 150. We got about 20 minutes. I want to do these three together. So get your books out. And we'll do those three together. Doesn't matter that they're out of order on your paper or not. Did you think I wasn't gonna be here today? Is that why you showed up?
No. I was here last time.
I know, and I wasn't here. That's all I'm
I
saying.
know.
Last two times, I've been absent twice on ground days, and you were here both those days.
Funny how it works that way.
I think you're calling in here and asking somebody, is he
Oh, yeah.
here?
I'm going out of my way to do that, Mr.
Cooper, did you lie to her this morning and say, no,
Yeah.
he's not here? Just so you could laugh at her when. Problem 20. I sort of have that. I don't know if I got another slide for the. Problem 20, the table shows the number of male and female students enrolled in nursing at the University of Oklahoma Health Sciences Center for a recent semester. So you got that table there. Find the probability, part A, find the probability that a randomly selected student is a nursing major. Probability that the student is a nursing major. So how many nursing majors do we have?
1,167.
Probability. Nursing majors, all right, if I abbreviate stuff so I don't have to write so much.
Yes.
Nursing major. That's probably not a good thing because the other says non, doesn't it? So major. Can't spell. How many total are nursing majors?
1,167.
And we're taking out of a total of how many students?
3,964.
Everybody agree with that? Yeah. That's your answer. Probably better with this one to change it to a what? Decimal. Somebody do that for us real quick. Go out 3 places.
0.294.
Everybody agree with that?
Yeah.
Now notice on that one, we're just saying nursing major, so we're taking out of the whole population that we're dealing with in the chart. Find the probability that a randomly selected student is a male. Probability that you pick a male. How many males are there?
1,255.
55?
1,255.
And how many total students again?
3,964.
Somebody divide that for us. What are you doing here, computer? It's flashing.
0.317.
About 32%. If 32% is males, could we figure out percentage of females fairly easily?
Yes.
32% of males, what percent's gonna be female?
68.
68%. Letter C, find the probability a randomly selected student is a nursing major given that the student is male. So this time, now it's a little tougher. We want a nursing major, but we're only picking from what?
Male.
The males. So given that the student is a male, what's the probability that they're a nursing major? Well, we're taking from nursing majors, so how many total are we picking from?
700, like you said. Everybody go.
Wouldn't it be 3,964?
No, it'd be 1,166.
So we're only looking at the nursing, no, I'm sorry. I'm saying it backwards. Let me read it again, make sure I get it right. Find probability at randomly selected student is a nursing major. Nursing major given that student is male. So we're given that it's male. How many males are we picking from?
1,255.
255?
Yes.
Is that right?
Yes.
How many of those are nursing majors?
151.
Does that make sense now?
Yeah.
After I screwed it all up, set it backwards. Somebody change that to a decimal for us.
0.120.
No, it's not right.
0.144. Something else is 151 divided by 12.
Is it one out, is it point?
I did it wrong. 0.120.
Alright, my fault. I was looking at it wrong. I was thinking it should have been lower than that. So about 12%. Part D, find the probability a randomly selected student is a nursing major and male. So now, we're picking, so they're a major and male. Is that saying the same thing that we just got done saying?
No,
No, because now we're picking out of what?
the nursing major.
So we went to nursing majors that are males, but we're picking out of what pool?
The one. You're the whole.
The whole thing. So how many total students did we have?
3,964.
And how many of those were nursing majors and male?
151.
Somebody divide that for us. What do we know about that event? That's unusual. Are the events being a male student and being a nursing major independent or dependent? So again, are the events being a male student and a nursing major, independent or dependent?
Independent. Right.
If they were independent, what should have happened with those last two?
Be relatively similar.
They should have been the same. So are they independent of each other? No, they're dependent because can you be a nursing major and be a male?
Yes.
Yeah. Which one did I say next? 20?
26.
26. 16 batteries are tested to see if they last as long as the manufacturer claims. 4 batteries failed the test. 2 batteries are selected at random without replacement. Find the probability both batteries fail the test. So you have 16 total batteries. Total. 4 failed?
Yeah, 4.
I thought I said 2. 2 failed out of the 16, right?
4 failed, 2 failed.
And we're picking 2 at a time, that's what it is. So we're picking battery 1, battery 2, whatever, 2 batteries. And we want What'd it say? Part A?
Probability that both batteries fail the test.
Part A is fail and A fail. What's the probability that we pick one battery out of the 16 that fails? 4 out of 16 times what's the probability that we pick a second battery after that that fails? 3 out of 15. We could reduce this down if you wanted to make it easier on yourself. That's 1, that's 4. This way you can reduce up and down also. That's 1, that's 5. What's 1 times 1? 4 times 5. Somebody change that to a decimal for us. 0.05.
I have a question.
Yep.
So if the 2 batteries are selected at random without replacement, is it safe to assume that the 4 batteries that also failed were not replaced?
Yeah.
Or should we assume that they were replaced? Because,
Yeah, it's just saying, all right, you got 16 batteries total.
okay,
Yeah, you know that the 4 failed. Well, they stuck them right back in.
okay,
So-
just the 2 that they recently picked were not replaced.
No, the ones that aren't, they're just saying, when you take this first battery, so we got the first battery sitting here,
Yeah.
out of the 16. We're not putting it back into the pile and then picking again.
Oh.
We're keeping it out and then picking another battery out of the whole pile.
Okay, that makes sense.
Yeah, I understand where you're thinking, if the batteries failed, why don't we just stick it back in the bunch? Which, find the probability both batteries pass the test. So we have the probability the first battery we pick passed and the second battery we pick passed. What's the probability of we pick 1 out of the 16 and it passes? 12 out of 16. What's the probability that we pick a second battery once we've taken that first one out? 11 out of 15. Somebody multiply all that for us. Go ahead, just change it to a decimal once you do the multiply. Multiply tops, multiply bottoms, and then divide the 2 once you get both your answers. Just give me the decimal answer. .55. So about 55% of the time, we're gonna get 2 good batteries. Part C, find the probability that at least one of the batteries fails the test. So we want the probability at least one fails. How could we do that? If at least one fails, that means 1 could fail or 2 could fail.
We already know the probability of 2 failures.
So we know that.
So we-
Actually, what we want to use is this one right here.
Right.
So probability is both passed, 55%. Well, that means if both passed, the only other things that could happen is 1 could fail or both could fail, right?
Yeah.
So how could we find the probability that at least 1? 1 minus 0.55, what's that give? 0.45. 45% of the time, we're gonna get at least one of the batteries if we pick 2 of them at random that fail the test, or that failed the test. Which of the events can be considered unusual? A. And our reason is it's 5% or less. Happen 5% or less of the time. Now back to, because we don't have a whole lot of time, I probably won't get to that, but back to what you were saying, you know, why would they put them back in? Well, if you're a business, you're testing these batteries, you might not, but if you're not a real high quality business and you really don't care, and you're shipping these batteries out to people, I'm shipping 2 batteries out to Jacob, 55% of the time, Jacob's gonna get 2 batteries that are good. 45% of the time, he's gonna get something other than that. What are they hoping?
That
That if you're one of these,
you don't send it back.
that you don't send it back? And a lot of times, does that ever happen? Yeah, I don't know. I got all kinds of crap sitting in my barn that didn't work that I think, man, I need to take that back, and then just completely forgot about it and didn't mess with it.